I know I print some stuff, for my job, trying to do something. Sometimes you can undrip it, and sometimes it's just gone.
It's called an upgraded one,
Yes. With your voice.
like my oscilloscope. And there was no response from the manufacturer. There's no way to find out the schematics. It might have been something simple, but have no way to even. Okay, we talk about phase noise, noise floor, image rejection, minimum detectable signal, signal to noise ratio, noise figure, and reciprocal mixing, and selectivity, and nonlinearity, and using attenuators. uh, One of the uh, receiver performance specifications is sensitivity. And now they use the term minimal discernible signal. When we talked about the A to D converters, and the least significant bit in there was divided, and when you divide that into whatever your reference voltage was, gave you the minimum discernible or detectable signal. So in the case of receivers, when they refer to this, whether it's a digital SDR type or it's an analog type, it's the weakest signal that you can detect. Well, not necessarily you can hear it, but the receiver will detect it. So there is some indication, maybe it probably doesn't even move the S meter, but can detect it. One of the things that affects that is the noise figure. And that's the ratio of the noise internally generated within the receiver itself compared to the theoretical minimum noise if everything was perfect and there was no noise generated, which I believe is minus 174 dB. I think it may be on a, yes.
I would think that this would be very, very important when it comes to some of these low signal quality digital modes, the ones that are really low level signals.
Right. Well, definitely it would have an effect. The more internal noise your radio has, the worse the noise figure is going to be, which means effectively you're raising the noise floor up. So when on the digital modes, a lot of times we'll be able to detect a signal that's 20 dB below the noise floor, but that's not the theoretical noise floor. That's the noise floor in the receiver, in the system itself. And it also is a function of how wide your bandwidth is, because the wider the bandwidth, the more of that noise floor power is part of the signal.
Thank you.
So what does the MDS of a receiver represent? What power level does a receiver minimum discernible signal of minus 100 dBm represent?
Well, I know the answer is 0.1 watts on it because I memorized it, but I'm not sure.
How do you get there? Okay. How do you get there?
Oh, just that.
it said it was minus 100 dBm. That's 100 dB reference to a milliwatt. Okay. So a milliwatt is what? Minus 30 dB reference to a watt. So 100 dBm reference to a milliwatt is actually minus 130 dB reference to a watt. Right? Milliwatts 1,000, so that's 30 minus 30 dB. So now that we have it in watts, okay, we have to find out.
There's just watts.
You do the old anti-log bit, okay, 10 to the power divided by 10, because when we do the dB formula, we multiply by 10 times the log. So we got to divide it by 10. You remember that, right? So there you go. And it comes out. And it comes out 10 to the minus 13. And everybody knows that's 0.1 picowatt. No. Well, you'll remember that one now, if you get it. What? Oh, did I back up? Let me see here. Or is there one out of order? I thought we did that one. Oh, got a slide out of order. So noise figure we said was the ratio in dB, or it's the dB of the ratio of the noise generated internally compared to the theoretical minimum noise. So what is the noise figure of a receiver?
No.
What'd you say?
Wait a minute. I got it cheated because I did the theoretical, but I see there's another one theoretical, so I should probably read them.
Yeah, read them all carefully. Let's try delta. Like I said, the noise floor is, I don't exactly know how they determined this, but this is standard minus 174 dBm per hertz. So as the bandwidth increases, so does the noise floor, because you multiply the bandwidth or the hertz times minus 174, which would give you a larger number, a more positive number. The example here is you've got a CW receiver that has the equivalent input noise power density of, and that's what they call the noise power density, because we're measuring power, of minus 174 dBm per hertz. So what were we missing here?
You know, it seems to me they get so specific with this minus 174. And they say a room temperature. What the heck is that? I mean, why don't they, you know, you would think that they had a very specific temperature range.
Well, I'm sure the room temperature is defined as, I don't know, 25 degrees Celsius or something like that.
In the Navy, room temperature is 74 degrees. It doesn't matter what that thing on the wall says. It's always 74 degrees at every Navy workshop.
Okay. I think in this example, they're showing you what the carrier would have to be to output a 0 dB signal noise ratio with 400 hertz bandwidth. So you take that, since it's 400 hertz wide, you got to multiply the minus 174 by 400 hertz. And that's what's down there in the example on how you get there. It's a very confusing example, and I don't remember the question. I don't think you have to do the math. We'll see. What does a receiver noise floor of minus 174 dBm represent?
Remember room temperature.
Yep. Oh. How much does increasing a receiver's bandwidth from 50 hertz to 1000 hertz increase the receiver's noise floor? So you're going to go from 50 hertz wide to 1000 hertz wide, which means I'm going to pick up more noise.
You can double it and so it's 3 dB and
Any answers? Thirteen 13 dB is 20, right? What's the ratio between 50 and 1000?
It's like that.
Huh?
You said it's 20?
Yeah.
because you double.
10 dB is what? 10, right?
Right.
3 dB is what?
Okay.
2.
Mhm.
Multiply them,
Right.
20. Yeah. You have to get used to playing with dB a little bit. Okay. Digital signal processors, most of the newer radios have them embedded at some stage in the audio section, typically, to help filter out noise and interference that's getting in as part of the signal. Usually you can vary or select different bandwidths. In some cases, you can actually, almost like analog controls, vary them instead of specific selections. The idea is that you want to pick the appropriate bandwidth for the signal you're trying to listen to. So if you're trying to do single sideband, normally would set the filter bandwidth around 2400 hertz or 25, whatever is available. Something that just encapsulates the bandwidth of the signal that you want without extra bandwidth. Like if you were doing CW, you might have it down at 100 or 150 hertz. The one exception to that is in the case of some of the digital modes like FT8, which is only 50 hertz wide, but there you do single sideband and have a 3 kilohertz wide because you're looking at the entire spectrum, basically, at 3 kilohertz wide and looking at multiple signals at the same time. Wherein you're doing CW or you're doing phone, you're trying to concentrate on a single frequency. What's an advantage of having a variety of receiver IF bandwidths from which to select? Sure. Charlie. Some radios have what they call roofing filters. Yaesu pushes their roofing filter. I really tried to get an understanding of why a roofing filter is different or better than a bandpass filter on the front end. And I can't find that there's any difference except marketing, because a roofing filter sounds like, well, that's cool. But all you're trying to do is filter out other signals in the front end. So whatever you call it. And if you've got a very strong signal close to the one you're trying to listen to, it could cause either an overload or some blocking or desensitization. Yeah, that word. Of the signal. So the narrow band roofing filter, which is a narrow band bandpass filter, will help improve the dynamic range, the blocking dynamic range. So how does a narrow band roofing filter affect the receiver performance?
What you just said, Johnny.
Yeah. Charlie? Image rejection. It used to be a harder thing to solve back in the old analog super heterodyne radios, and they typically had a 455 kilohertz IF frequency. So you wound up with signals that could be very close together because of that. Where'd my mouse go? So if you had a strong signal that was exactly 2 times the intermediate frequency away, okay, you could possibly hear that signal because of the way the mixer works, where you're seeing some and different frequencies. And I think the example here is trying to show that if you were tuned to 14.3 megahertz and you had a 455 kilohertz intermediate frequency, and it means your local oscillator in the radio is going to be tuned to 14.3 plus 0.455 to give you that offset. If there's another signal that was at 15.210, and you use that same local oscillator frequency, you're going to get a 455 kilohertz signal, which is the IF signal. So you're going to hear both of them. So that's why you need ways to filter out the signal that, in this case, the higher frequency. So you'd kind of want a band pass or a low pass filter so that you could block that 15 megahertz signal. Some of them have some radios have what's called a receiver IF shift. And I think that's effectively, on my ICOM, they call it passband tuning, where you can adjust the IF filters. And it's kind of like 2 versions of it where they're superimposed, and you can shift one left or right and the other one left or right. So you can narrow the pass band, or you can shift the pass band and kind of move it around. So you can select not just the width of the filter, but the placement of the filter. What is the purpose of the receiver IF shift control? Charles. One of the ways to improve image rejection is to start using a higher intermediate frequency. So it makes it a lot easier. The farther away those images are, the easier it is to filter them out. So that's where the front end filter or pre-selector, in some cases, I've seen them where you can select different front end pass band filters for different frequency ranges. It automatically will do the band pass filtering depending on what band you're actually looking at. Which of the following choices is a good reason for selecting a high IF for a super heterodyne HF or VHF communications receiver? And that's really true whether it's an SD analog superhet or an SDR. You basically have the same issue that you have to take care of digitally. Which of the following receiver circuits can be effective in eliminating interference from strong out-of-band signals? Alpha.
Bob,
Yes,
you and I think we both have a 7300. Is that true?
that's true.
Okay. Do you think there's any benefit to getting an outboard pre-selector?
I don't know. I solved the problem by getting a 7610.
Okay. All righty. Thank you.
But I still have the 7300. Not sure what I'm going to do with it. Okay, phase noise. Phase noise is just, I call it phase jitter, where there's slight variations in the phase, or some very small phase shifts of the signal. That's called phase noise. It's kind of inherent in the oscillators themselves. When noise gets in there, it can affect the tuning circuit and enough to actually just change the phase, not necessarily the frequency. You'd have to change it by a whole wavelength basically to shift the frequency. It's just another thing that can cause interference, even though it's a very small variation. I mean, it multiplies itself, so you get a multiplied phase noise on the other signals. And they call it reciprocal mixing. I think that's the only one you really have to remember is the name. So what is an effect of excessive phase noise in an SDR receiver's master clock oscillator? Delta. What is reciprocal mixing? Delta. Okay. SDR nonlinearity. SDRs use analog to digital converters at some point. There's some hybrid versions where they actually do some sampling and detecting, generating IQ before the A to D. In some cases where it's called direct, where the RF signal comes straight into an analog to digital converter. And the linearity of that A to D converter will have an effect. And it's because in most cases, you just can't manufacture a perfect device. So it will have some nonlinearity. So every sample for that A to D converter may not be exactly a multiple of what it should be. Could be off a little bit. So it gives you a nonlinearity in the output, just like if you were going through an amplifier, an analog amplifier, which didn't have a linear amplification curve, then you get a nonlinear output. You have the same kind of effect with an A to D. Not as much, but you still can have that effect where when you sample it and then if you look at it converted back to analog, it's not going to be a true representation of the signal that was sampled. You can also have overload. If you remember, if with the A to D converter, you've got a reference signal, which is the maximum signal that it can detect or will detect. So it's from the maximum down to the minimum signal level, depending on the number of sample bits. If say 1 volt as your reference for the A to D, and you had a signal coming in that was higher than a volt, the A to D is still going to tell you this 1 volt signal, even though it's 1.5 volts. So it's saturated or overloaded. And, whatever the maximum output of the A to D is all it's going to tell you. So you're just going to hit. And if you looked at the samples, you just see a flat top, like they'd all be the same. An SDR receiver is overloaded when input signals exceed what level? Attenuators. A lot of radios have a built-in attenuator that you can switch in, usually in the front end. I think the 7300 has 2 levels. I forgot what the ratios are, but it's either in or it's attenuator 1 or attenuator 2. And when you have a lot of atmospheric noise and you're like down on 80 meters where noise is a big problem, you might want to use the attenuator because there the signal strength isn't nearly as much an issue. So why does the input attenuation reduce receiver overload on the lower frequency HF bands with little or no impact on signal to noise ratio? Delta. I don't know. They say atmospheric noise is generally greater. I'd say it's always. A miscellaneous question. FM receivers, and we hadn't talked about those in a bit, have what's called capture effect, where because of the way the discriminator works, if you have 2 signals close, one's much stronger than the other, you will only demodulate or discriminate the strongest signal. Whereas in AM, if you have two signals very close together or even on the same frequency at different amplitudes, you would hear them both, one louder than the other. What is the term for the suppression in an FM receiver of one signal by another stronger signal on the same frequency? Ooh, we're almost done.